Hi, in this video we are going to discuss about FIR filter structures. We have been discussing filter structures, but now in this video we'll be discussing FIR filters, which means they only have zeros and no poles. Okay, so this is how it looks like. My Y of n, let me just remind you what are FIR filters. Basically, my H of n is finite. That is why it's called finite impulse response filters. So therefore my H of Z has only zeros, no poles. Okay. So I can write my filter like this. Yn is H naught times xn plus H1 times xn minus 1 plus so on. Uh, so this has got 4 terms up to H4. So it's a 4th order filter. Now I can represent it like this. So x times H naught, right, plus xn minus 1 times H1 plus xn minus 2 times H2 plus xn minus 3 times H3 plus xn minus 4 times H4. This is a very simple representation structure. It's called tabbed delay line. So it's a direct form. It's called direct form, specifically tabbed delay line. Now if I take a transpose of this, you remember from last video what is the meaning of transpose. So let me draw it for you. Basically you convert your dots into plus and your reverse the direction of input and output, and your adders become dots, basically splitters. So it will become something like this. So if I were to maybe I will write again. So x will become y and the directions are reversed. This becomes an adder and h naught is now pointing upwards, right? And this becomes just a splitter. So I'm sorry, this is h1 is pointing upwards, and this z inverse remains same here, and there is an adder here, right? And then again a z inverse, and again an adder here. This is h2 which is reversed now. In this way I keep going and until my input is x, right? So if you compare with this, like just reverse the whole thing now. This is x, so there you have h naught closest to y, right? H naught was closest to y, and then z inverse, and h1 was closest, next closest, then h2. In this way it goes on up till h4. So basically you same thing can be written like this, right? So this is the transpose system. So what is the advantage of using this transpose system? The advantage is that we can reuse the delay line if several inputs for single output y. So basically, if I want to feed in many x, like this is x1, then x2, then x3, then those structures can be simply put in here, right? And then I can reuse this line. So that means more efficient implementation, right? So let's see the next structure, which is a cascaded structure. Cascaded means in general, if you have an h1z, h2z, you can break it down into, so this is the h1z, h2z, you can break it down into h1z, then h2z. So now instead of implementing the complete system, you implement two separate systems and then cascade them or put them in series. So this is series, right? And how do you do it? So for example, if I have got two zeros which are complex conjugate of each other, I'm sorry, two zeros which are complex conjugate of each other, then you cannot implement this. You cannot cascade these two together because each filter will have complex coefficients and you may get instability. So it's difficult to implement. So what we do is whenever we get complex conjugates, this is for real H, right? So whenever we get complex conjugates, we will put these together into one H1. So it means we don't separate them into two different H blocks, but in the same block we put. That is why we are factorizing into second order sections. So my each section, like this is one section, it could be either first order or second order. If the pole or zero, in this case the zero only, if the zero is on the real axis, then no problem, it could be a first order section. But if it is a complex conjugate, then take those together and put them into a second order section. So second order section is also known as SOS in short, right? Um, now let's say this is a this is a third order system. I can split it into roots, right? In Python, you know how to compute roots. We discussed in previous videos. You found the roots, and now you found that this zeta1 is a complex root, and zeta1 star is the conjugate of that zeta1. Okay, so you won't implement three systems separately, but you will implement these two together as a second order section and this one as a first order system. So this is how x is first multiplied with h naught, and then so 1 minus zeta naught z inverse, so this is the thing, and then 1 minus 2 times real times zeta 1 z inverse, so this is the thing, and we find that here we should get a negative sign, right? So this is the simple implementation. So this is my h naught, this is my h1 of z, this is my h2 of z, and they get multiplied, right? So don't confuse that this is getting transformed in the time domain because it looks a little confusing, but this is, consider this as an h1z and this as your h2z. So this is my h1z and this part is my h2z, this brackets. Okay, so this is the cascaded filter structure. Now let's move on to another kind of filter structure, which is called linear phase filter structure. But this is applicable for symmetric filters. So symmetric or anti-symmetric, right? Symmetric or anti-symmetric. So this example is for symmetric, where Hn is h of n minus n, capital N minus n. Okay, so now what I can do is, since this is symmetric, I can group these terms, right? I can group this one with this one, and I can group this one with this one, and this is what I get. So this is okay. I will just to show you the correspondence, I'll use the same color. Xn plus xn minus 4, xn minus 1 plus xn minus 3 plus xn minus 2. So the b naught can be common. So remember I told you that if you want to have computationally efficient systems, then you take many terms common as much as possible. So we have taken out b naught as common. So this is how it looks like. You have xn plus xn minus 4. So xn, so this is rotated, right? So this is a rotated thing. So you need basically, if I have to draw it in plane, this thing, then let's say this is a z minus 1, again a z minus 1, again a z minus 1, again a z minus 1. So this is xn as the input here, xn minus 1, minus 2, minus 3, minus 4. And what you are doing is xn plus xn minus 4, you're adding these two, add, and the output is getting multiplied by b naught. And then you have taken xn minus 1 plus xn minus 3, xn minus 1, xn minus 3, added them up, and the output is getting multiplied by b1. And then you got xn minus 2 simply, and no adding here, and then you multiplied with b2, and then all these outputs were further summed over to get yn. So this is the intuitive way to draw it. but so these are all z minus 1, right? But if you rearrange it, it becomes same thing, right? Okay, so the advantage is that we are using half as many multipliers, right? Because we have taken things out common, so you have half the number of multipliers required. This makes your computation fast, and you also need to spend less money, right? Because you can now, with half the multipliers, you can do the job. Okay, uh, so this, you can convert this into transpose form also, which is very simple concept, and that has some benefits as we discussed in the previous slide. Okay, now we come to another kind of implementation of FIR filters, structures, which is called polyphase decomposition. So let's see what is polyphase decomposition. Basically, here you make use of a fact that you can group terms which are um, uh, multiples of like a decimated version. I will show you that. Let's say you have h0. I want to decompose it into three separate filters, let's say. So what I will do is I will group h0, h3, and h6, right? And I will group h1, h4, and h7. And similarly, I will group h2, h5, and h8. So you see they are all, so h0 plus 3 is h3, plus 3 is h6. So they are differing uh, by a common difference of 3. And similarly here, h1, h4 difference is 3, h4, h7 the difference is 3. Okay, so let me write it down. So my hz becomes, this is equal to uh, okay, h naught plus h3 z to the power minus 3 plus h 6 z to the power minus 6. So plus h1 plus, sorry, there was a z inverse, I'll take it as common. h1 plus h4 z to the power minus 3. So this is, let me take it in bracket, plus h7 z to the power minus 6, and z inverse is common, plus h2 plus h5 z to the power minus 3 plus h8 z to the power minus 6, and z to the power minus 2 is common. Okay, so what we see is, so I can write it like this. This is equal to some E naught, so this can be written as z cube plus E1 z cube z inverse plus E2 z cube z inverse. So where my E naught z is simply h naught plus h3 z inverse, because the cube factor is gone, plus h6 z inverse, sorry, z to the power minus 2, right? And similarly I can write E1 and E2 also, right? Which E1 will also be in terms of z1 and z to the power minus 2. So all of these are second order filters, second order sections or second order filters. Oh, actually, this need not be only second order. It could be higher order also. So I won't write it as a second order section. I will just say second order filter. It means it could be any order. And the advantage is that now let us look at the implementation part. So it looks like this. I have my x, which is the input, and I will have my x goes to h naught, okay, let me first write down the basic general form. So it is like this. So I have my uh, e naught z cube. Okay. Okay, let me say it goes to h naught, and then you add it with h3 z to the power minus 3. Let me create. How do I create? Okay, let me say this is z to the power minus 3, and then again z to the power minus 3, so that we can get z to the power minus 6. So here the output is this is my xz z to the power minus 3, xz z to the power minus 6. Okay, now I want this multiplied by how much? H3, and then I need this multiplied by H6, and these outputs, they get summed up, right? As you see in the previous slide. Sorry. Yeah, so they get summed up and they get added finally. And this output goes to Y. Okay, and then we have H1 plus H4. So I need to have H1 times, okay, we got xn, and then we need this term with multiplied with h4, and this term multiplied with h7, right? And we add these outputs, and the output, what you see, the output has to be multiplied with a z inverse. So I multiply this with z inverse, and the output gets added to phi, right? And similarly now I have to do for the third part, which is h2, h5 and h8. So I have to have h2 and from here I have to get h5, and from here I have to get h8, get all added, and again this has to be passed through z to the power minus 2. So we can be little clever here, that instead of making a separate function of here, I can just put this output into this, and then it automatically gets multiplied with z inverse, with another z inverse. I'm sorry, I have to introduce one extra z inverse in between, so that it ultimately becomes z to the power minus 2, right? And so I know this looks very messy, but you can clean it up. Okay, so this is how polyphase decomposition looks like. But now, why are we doing this? Okay, so one obvious advantage is that, see, you have reduced the number of components required. Instead of having uh, 3 plus 3 plus, you have 8 delay components, but you are only you only need only 4 of them because these are grouped together, right? Um, but a major advantage of polyphase decomposition is that it is very useful in efficient decimation, and it is very useful in which is very useful in multi-rate signal processing, which is popularly used in communications. So imagine this situation. So you have x0, x1, x2, basically your input signal. You process it with some hz, then decimate it, let's say by a factor of 3, and then you get the output. This is very inefficient because you're throwing away almost 66% of the samples, right? But this is more efficient in the sense that, so you're doing 66% extra computations here, right? But here you reduce your computations. Uh, you do by with the help of polyphase decomposition. So this branch has got only x0 and x3. This branch has got only x1, x4. This branch has got only x2, x5. So in this way, we have and I'm switching. Let's say my x0 goes here, x1 goes here, x2 goes here because um, my um, y is basically decimated version. So my y0 and in the original, let's say the undecimated version, the y0, y1, y2, y3. So I have to throw away y1, y2, right? And this is my y decimated. This is y0. This is y3 basically because it's a decimated version. So this is y3. But I am throwing away y1 and y2. That's why I'm not. I need not put those here. So my y0 is computed from uh, these values. Okay, so this is how it makes the implementation very efficient. So this was all about FIR filter structures. In the next video, we'll be seeing infinite impulse response filter structures. Thank you very much.